that's something which you have to keep in mind, that you will come across minus signs, you will come across I signs, and you don't have to be worried about it. They are amplitudes, quantum probability amplitudes. Okay, so here now I'm just rewriting this 3-qubit system separately. It's just rewriting them. So there's no deep understanding involved here. It's just a simple rewriting mathematics. I'm just taking the common, because if you look at these first two terms, have the third qubit is in state 0 in both these terms. So what I'm going to do is I'm just pulled out the third qubit term here, 0, and then the first two qubits are written in superposition of this form. And again here we have done the same thing. In both of these, the third and the fourth term, one is the common term in both. On the third qubit, I'm taking this out and I'm rewritten them. So now the probability that the measurement outcome is 0 is this. It means that if I make a measurement on the third qubit, this is what I'm going to get. So it means that I'm taking a mod square of this whole term and then say with probability of I'm going to get my third qubit as 0. And in this case, the resulting superposition would be this. So it means that this is what would be your output, final output with half probability. And the probability of measurement outcome of 1 is also, you see, just because you have minus n, nothing happened. Because these two are of different bases, and then you take mod square of them, then you will still get 1/2 probability. Similarly, the output state will be these two. So if I'm making measurement only on a third qubit, I would still have some quantum state, which means my output will still be in superposition. So here I didn't make a complete measurement on this system. I only made a partial measurement on the third qubit, and I'm getting some partial information out of that system, and I can use that as a continuation for algorithms. So I'm not making it completely classical by collapsing into just one of the possible states. I'm trying to collapse it into one of the subspace. That's what we call subspace of the 3-qubit system, and I still have a superposition. See here, you collapse into this particular state, but still you have the probability amplitudes summing up to 1. So you take square of this mod square of these two terms, it will still be 1. The square of mod of these two terms will still be 1. Right? So even if you make measurement on the subspace just only on the third qubit and you get a quantum state as an output, your amplitudes modify a bit, but you will still have this normality satisfying. Okay, so there's some question which been asked, like why are you getting this √2 term? Okay, so I think you should take this as a simple exercise which you're looking at. When I say, so you make a measurement of this, and then we wrote in yesterday's lecture that you always have to normalize. You introduce a normalization condition for your measurement operators. So when we wrote measurement operators, we said there is some way you are normalizing. You're going to divide it by the whole terms and then multiply and divide by some particular term. I think I'll try if I can go back to that term. Yeah, here. Right here, that's what we write here. So this is my measurement operator, which we had discussed yesterday. So you can make measurement on the subspace, and there are this condition which you take on both the possible subspace. You need to look at to satisfying the completeness equation, and then you are going to get a square root of it. It's a simple exercise, but you can just revisit and then see how you are normalizing your vector state of it. So here, as we said, you can you always normalize, and then you get a complete quantum state out of your measurements. In fact, it becomes obvious when we are trying to look at few other examples in coming slides. Okay, so in addition to state preparation and basic quantum logic gates and measurements, I think that's if you are just taking home the message of where quantum mechanics plays a different role than the classical mechanics in the initial state preparation, during the process, and measurement, you have got a very good overview of what quantum computers or what quantum mechanics is doing to your whole new way of thinking. So that's something which we have looked at, right? In a state preparation, they can be in superpositions. In an operational ways, in the dynamic defining, we discussed that it has to satisfy unitary conditions, and then there are some set of quantum logic gates which are required to define the dynamics. And in measurements, we are collapsing, and you can also choose to do some partial measurements, and then you can look at it. So that's what, when state preparation, dynamics, and measurement. So we have tried to cover the sub ingredients of these three important features in defining the whole processes of operations, or doing tasks, or running, or running some useful processes in the machine. Okay, so now comes quantum circuits. So we need to start this, one of the important topics which comes in the field, because first you have a problem. I think if I want to think of some problem that I want to take it to quantum computers and look at it, then my first would be a very normal language, right? I define a problem in a statement. After that, I'm trying to define, you put in some effort to define the problem in a mathematical term. So what is your initial state, and what should be your set of operations, and what should be, how are you doing operations so that you get your results. So once you have convert your verbal question into some mathematical form, then you start looking at the basic gates required to define those set of mathematical operations. Sometimes you might have to do some approximations, because the operations you need may not be the quantum logic gate. So you do some approximations, and after that you start converting them into a circuit so that it becomes visibly clear of your input state processes and output. So from defining the problem from a mathematical side, from a verbal side to mathematical side, now we are moving into a circuit model where you convert them all into some kind of simple graph structure, a visual structure. There are some examples here. I'm going to look at some few very useful examples, and we'll see how far we can get into it. So this is just an Hadamard transformation applied on a single qubit. It can be any input state. You look at it. So if the input state is psi, the output state would be operation on that psi. So here it's both the ways. So one of the important thing about these operators, quantum operators, are because they are unitary, they are reversible. Which means if I take state 1 and I apply an Hadamard operator, I get this state. If I take this state, that is 1 by root 2 0 minus 1 by root 2 1, and I apply a Hadamard operator, then I'm going to get state 1. So they are reversible gate operations. So both ways it works. If I begin with 0 here, then this minus sign will be plus sign. So this is what defined as an Hadamard operator. Now measurements are indicated by circles or ovals, and this is the way some people also put it in a detector form. But you have an input state, you have an Hadamard operator, and you make a measurement. The moment you make a measurement, from going to the single line, which is a quantum channel, to a classical double line representation, you have no way to go back and recover state 1. So this is reversible only within this quantum levels. So when you have quantum state, Hadamard operator, and then you can again go back to state 0 by inversing this operator. But after you make a measurement, there is no go back. You can't go back to the results out of measurements is a classical value, and as in the above end, we draw a double lines to indicate the classical bits. So this is something which is used to represent Hadamard gate and a measurement operator. Similar way, you can always all single qubit gates, you can write them as X, Z, and everything will be here. So now we'll take a multiple qubit here. Again, a multiple qubit gates are generally represented as by rectangles, and they have their own special values. It can be any state A, state B input. It can be 0, 0, or 0, 1, or 1, 0, or 1, 1. Or it can even be superposition. A itself, when we said in the beginning of quantum computers, today's lecture, we wrote some state S can be written as superposition of all possible things. So it can actually be equal to some alpha 0 plus beta 1, my input state. So it can be any possible quantum state. So here I have a control NOT gate, which says if my state A is some value, then the output state would be addition modulo B, which means that if this is 0, this will be 0. And if B is 1, this will remain 1. The output state will, because 0 plus 1 will be 1 itself. But if this is 1, and if this is if A is 1 and then B is also 1, it flips. So you can get a flip. If this is 1, then this will be 1 and this will be 0, and that will be flipped to another state, which will be 0. So here is an action that indicates classical input A and B. Also similar lines, a controlled control NOT gate. So you can actually see if both A and B are 1, then you will have an addition modulo to C, or else you don't have. That means that if this is also 1, this is also 1, only one, then you are going to flip C, or else you are not going to flip C, you will keep it as it is. So this is another example of representing 2 and 3 qubit. Here is a very interesting example, which it has been detailedly worked out, but you can see why circuit diagrams. I mean, this actually gives an idea of why writing quantum circuits will be very useful in quantum field of quantum computation. Right? So we take a simple example here, both 0, 0. So this is a circuit, so we don't have to worry about it. I mean, it's just on both the qubits, you have an Hadamard operator, and then you have a controlled NOT gate, and then again you have an Hadamard operator. That's all. We are going to analyze them after every operations. It's an initial state, after doing an Hadamard on both, after doing control NOT, that is psi2, psi3, psi4, and we see what will be an output. Okay. If my initial states are 0, 0, if I begin with 0, 0 at both, and then I do an Hadamard operator. So the psi2, which means that after I do this operation, this is the output I get. So we have done an Hadamard operator here. It's in superposition of 2. The second qubit is also in superposition. All that we do is simple math of multiplying both of them. And this is the output we get. 0, 0, 0, 1, 1, 0, 1, 1, both of them, all the 4 of them with half probability. Up to this point. Now we are doing this control NOT gate. So after we do this control NOT gate, here we can see that first term, nothing happens because both are 0, 0. Second term, my first qubit is state 0, so nothing happens to this. But the third term, since my first qubit is state 1, the second qubit flips to 1. Right? The third one, my first qubit is 1, so second qubit flips from 1 to 0. So you are seeing the flip in these two elements. The second qubit is flipped into these two. So if I'm again rewriting them, again, I mean, just like backward way of, I mean, you are applying, sorry, what we do is after this psi3, you are again applying an Hadamard operator then. We have not written the state explicitly, but you can redo one more intermediate step for yourself. And then you can see you have 1 by root 2, 0. You will end up getting 1 by root 2, 1. And then again, the same thing. So you have got back the state you started with. So this operator, Hadamard on both, control NOT gate, and again Hadamard on both, is giving you back exactly the state you started with. But now let's ask, is it same for all states? So no, it's not same for all state, because this is second example we are looking at here. Instead of starting from 0, 0, if we start from 0, 1, like my first qubit is state 0, second qubit is state 1. This is the second example which I have here. So if I'm starting with this example, I repeat the same process. I mean, I apply an Hadamard operator and I get an output. Here you want to also get a minus sign here. You can see because of this 1, Hadamard operator introduces minus sign on state 1. So you have this minus sign on both of them. And because of this minus sign, so you are getting some modifications to the states, and your output will be 1, 1 instead of 0, 1. You start with 0, 1, but it becomes 1, 1. Okay. So we have two more examples, right? Because just to see, analyze them thoroughly. So 0, 0 will not change. It will remain the same. But if it is 0, 1, it will change to 1, 1. But we have two other possibilities. That is 1, 0 and 1, 1. If you do a similar exercise of starting with 1, 0, nothing happens. Even though you have Hadamard on the first qubit, you do this operation Hadamard on both, control NOT, again Hadamard on both, you get an output of 1, 0. But if you are starting with 1, 1, then you repeat the same process, you are end up seeing 0, 1. So 1, 1 becomes 0, 1. So now carefully, you look at the 4 outputs we have got. Come on, you just think of the 4 inputs we had and the 4 outputs we had. 1 0 does not change and 0 0 does not change, but 0 1 changes and 1 1 changes. How is it changing? It is changing as a reverse of this control NOT gate. So if you're looking at this, control NOT gate changes the second qubit depending on the state of the first qubit, but whole of this operation does simply this. We have a Hadamard operator, control NOT gate, and a Hadamard operator on both of them, and it does a reverse of it. Now, this is actually very important in today's quantum computing era, because what we have now are very small qubit machines and people are trying out experiments and want to do some things on it. So sometimes you end up looking at a physical problem and then you want to see this is the mathematical operations of it, and then after that you convert into quantum gates, and then you will realize some of them end up having these complicated forms of circuit, and you can reduce them into a simple equivalent operation. So it's like what we call of reducing the complexity of the problem, or we call a shallow depth quantum circuits. That is the terminology which we are using these days, because you want to use minimal number of gate operations and then do some kind of computation process in that small available machines these days. So this is one of the simple examples, and you can actually have many examples. And in fact, that's one of the challenges these days. Can we reduce the complexity of a circuit for any given problem? Right? There are many problems people thought about it, and there are many papers available defining quantum circuits of them and how you can take these quantum circuits and look at it. But if we take those circuits to an experimentalist or people who have quantum computers and say them, oh, this is what solves one of the big problem, can you implement them? They say, oh, this is very, very complicated circuit, we don't have an hardware ready for it. So if you try to work on simplifying some parts of the circuits, you can always start working on simplifying them. And this is one of the simple example, and there are many things which people have done in the same lines in simplifying circuits. So you should keep in mind that you can do them both mathematical. Actually, sometimes you can look at the matrices multiplications and then you can do them, or you can look at them in a simple form of how you can use circuits and then simplify them. Okay. So now, I'm not given a complete detailed complicated ways of various possibilities of quantum circuits on multi-qubit systems and all. We just want to have a basics of quantum circuits and try to take 1 or 2 simple examples and try to understand advantage of quantum states and quantum computing. A very simple example, might not be dramatic ones, but that still shows the importance of it. So here is one very prominent, very early examples. It's called a superdense coding. The definition of superdense coding is here. I think since many of you are from computer science background, probably you people will appreciate it more than some of the physicists, some of physicists. Here, the simple example of superdense coding is this. It's a combination of, it's something using a classical problem and solving it using a quantum computer. Alice and Bob are in different parts of the world. So they are separated physically in different parts of the world. Alice has 2 bits, and we are talking about classical bits here, like for the beginning. Alice has 2 bits. It can be represented as A and B. It can be 0, 0, 0, 1, which are binaries, right? It's not quantum state, 0, 0, 0, 1, 1, 0, any of the possible configuration. She would like to communicate these 2 bits to Bob by sending him just 1 single qubit. And that is how this problem is defined. So to send 2 qubit, to send 2 classical bits, you have to send 2 qubits. In fact, in today's quantum error correction, classical computation, to send 2 qubits, you actually send more than 2 qubits. You encode them as a computational logical bits, and then so that it corrects for the errors and everything. But here, what it's saying is there some possible way of sending a single qubit which has information of 2 classical bits? So it means that reducing the resource. That's exactly the question which has been asked in this superdense coding problem. So Alice cannot encode 2 classical bits into a single qubit straight away. Simply if I say you can't, because we mentioned something, superposition, right? We can actually write alpha 0 plus beta 1 together simultaneously, but they actually collapse when you make a measurement. When they are collapsing, it means that your output will only be A or B. All right? Even classical information which comes out after measurement is only A or B. You are not going to get two classical information the moment you make a measurement on a quantum state. So, which means, in a simple terms, you can't straight away take two classical bit, encode them using a single quantum bit, and get an output. But there is some other way of doing it. So, what is that other way? So, this can be accomplished with an additional resource, which is an entangled bit. So, instead of using simple quantum bits to send, you can use an entangled bit in the beginning itself, and then you can send only one quantum bit from Alice to Bob, and which will have an information of two classical bits. Okay, this is one of the simple or a very early examples from a computational side where we see the advantage of using entangled state. So I think yesterday somebody were asking, why should we worry about entangled state? What is the advantage? This is very simple. You may not be able to appreciate it. Oh, this is not a dramatically, something which is going to change the whole of thing. But in a simple way, we see the impact of entanglement. And once you make things complicated and start building it, they have a bigger impact. Okay, so we'll work out these possibilities simply. I'm going to see the way. This is just a construct of it. So let's say Alice and Bob are physically separated. It means that they are living in two different worlds. Alice and Bob are physically separated. But before they separate, or in some way, in the beginning itself, they share an entangled state, which means that Alice has an information of the first quantum bit, and Bob has an information of the second quantum bit. Since they are in superposition, you can't write them separately. What is the state with Alice and what is state with Bob? It is a combined superposition state between them. So this is your initial state preparation. So you are not yet decided what are A and B to send itself. We are not even thought about it. We don't even know whether it was for superdense coding or not. You just have Alice and Bob initial itself. They share some entangled state between them and they are physically separated. So this is an initial state preparation. Now we will see what to do with it. Okay, if A is equal to 1, it means that if Alice wants to send A and B, okay, so that's what we look at here. A and B are the pairs, right? Alice wants to decide some modifications, wants to do some operations for the qubit with her, such that instantaneously some changes happens to the state with Bob, and so after that she does send it, and then they get an output of it. So how we do this as an operations, we'll see here. It involves few steps, and you have to look at each and every step. If A is equal to 1, right? Because Alice knows what she has to send. It's not that she's sending any information which even she does not know. Alice knows what are the values of A and B which she has to send. Only Bob does not have any idea about it. That's all. So if A is equal to 1, Alice applies sigma z operation on the qubit on her side, right? On the qubit A. If A is equal to 0, she does not do anything, right? If B is equal to 1, Alice applies this transformation, which is a flip, and that is 0 becomes 1 and 1 becomes 0 on a qubit A. And if B is equal to 0, she does nothing. That's what she does from her side. And Alice sends the qubit A to Bob. So this is the only qubit that is sent during the protocol. So that's what she's doing here. All that she's doing is she wants to send some information A and B, and then this is the state which she is sharing. All that she does is, depending on what values of A and B she wants to send, she does these two set of operations on the qubit with her. Whatever operation she does on her, she will send it to Bob. So the only qubit with her is the first qubit. She does these two operations and she sends it to Bob. Now, what will Bob do? Bob will apply a control NOT gate operation on the pair he gets, right? So I think it's we'll also appreciate, you'll start appreciating quantum circuit in the next slide, but then for the time being, you can just see it might look bit tricky following the whole step. Bob applies control NOT gate on the pair of A and B, where A is a control and B is a target. Now Alice has nothing. Alice did 2 operations on the qubit with her side and he has already sent it off to Bob. She had only 1 qubit with her. She did 2 operations depending on what she wants to send. If she had to send 0, 0, she does no operations at all. She only sends whatever she had with her. But if she had to send information of 1 in either 1 or 2 qubits, then only she is doing these operations. Bob will do a controlled NOT operation on, see, Bob now has 2 qubits with him because 1 was with him from before. Alice is sent to another qubit and she does this operator. After that, Bob applies an Hadamard transformation on only A, the qubit which Alice had sent. And Bob measures both A and B, and output will definitely be A and B. Okay, so now we'll see. These are the 6 steps. I mean, it's actually looks like 6 steps, but in a simple form, we have put it in this form. Operations are defined here. You can see how it is. If Alice wants to send 0, 0, right? She does nothing because this is what was the initial state they shared. So she does no operations on her side. And after step 2, there won't be nothing because she's only sending 0, 0, right? She does not do any operation on the qubits on her side. But Bob will do a controlled NOT operation, right? And then he does an Hadamard operation on it. So which means that he does an Hadamard operation on the first qubit, he gets an output 0, 0. So Alice had sent only 1 qubit. This was the input state, and this will be an output state on the Bob side. So by sending only 1 qubit, Alice has managed to send the information of 2 classical bit, right? Again, here same thing. She wants to send 0 and 1. As we said in the last slide, if she has to send 0, she does nothing. That's what she's doing. She does nothing on the state. So it will be the same initial state. But in the step 2, she wants to send 1. So what she will do is she will apply the flip operator, sigma x. So which means that 0 becomes 1 and 1 becomes 0 on the qubit which she has with her. So that's what you see. Nothing happens to the second qubit, which is with the Bob, only the qubit with. And then there is this step 4, which we say Alice sends both to Bob and a controlled NOT gate, not be done here. So it means that I think first step 4 and 5 are, sorry, you should actually see that the 4 and 5 are combined in this step. So doing control NOT on this, which means that it becomes 1, 1, 0, 1 remains 0, 1. It does not flip. So you will get 1, 1 and 0, 1. Now in this, Alice only does Hadamard operator, sorry, the Bob only does Hadamard operator on the qubit which Alice has sent. The output will be 0, 1. So similarly, if you just look at follow the 4 step, you are getting this output. You are only having phase. Once you make a measurement, you don't have to worry about the phase. All that you are interested is an output. So when Bob measures at the end, it's very clearly you are having an output of it. Output of what was sent. So here we are only talking about a simple way of sending 2 classical bits and with a minimal resource of 1 quantum bit. There are very advanced way of expanding this super dense coding, and people have looked at minimum number of what we call as n number of qubits required to send x number of classical bits. So what is the optimal form? What is the minimum resource required? And people have looked at it in a more complicated way and then have tried to understand this problem. Now there is this simple circuit representation. I said, right? We think going to quantum circuits helps you a lot from the way we had looked at it. So here we wrote down this as a 6 steps. We said A is equal to 1. This is what I said initially, right? You have a problem, which is in this English statement of a problem, and then you start trying to see what are the mathematical operations forms you are going to define a problem, what are the conditions you specify them, and then you can do those calculations. But when you go to quantum circuits, it's all same thing. Everything is explained here, all the 6 steps. A and B are the 2 classical bits. This is what is with the Alice side. Alice does this conditional operator. This is a control sigma z operator, which is it. Only if my first qubit is, sorry, classical bit information is 1, she makes a phase flip into the qubit on her side. Or if your B is equal to 1, you make some control NOT gate on the quantum bits on her side. After that, she sends it off to a Bob. So here we can see this only qubit with Alice is sent to Bob. This is the world of the Bob. The moment it is sent to the Bob, there's nothing with Alice, everything is gone. But she has already encoded the information of A and B in the single qubit state. Okay. So after that, you are doing a controlled NOT gate. Bob does a control NOT gate and an Hadamard operator, and you get an output. I think there's one question. Let me see, what is this last question of state after 4? One example. Okay. So you mean the state after 4th step? This exact. So here, in all these things, it is the 4th step. Okay, and the state after, sorry, 3 is missing. Yeah, okay, that's what I'm probably did here. What we did was sending is not put in. You are only having a controlled NOT operation. So here, from state 3 to state 4, you are only doing a control NOT gate, because that's exactly what is there in the diagram here, right? So after state 2, step 2, these 2 are the part which is done here. After step 1, state after step 2. So these 2 are something which is done in the Alice region. Step 3 is something which is sent to the Bob. So now step 4 is what is done here. Controlled NOT gate. So this is what we are doing. So it means that from this state, you are doing a control NOT gate. So here 0, 0, 1, 0. If you do a control NOT gate on this state, which means that only if my first qubit is 1, you are flipping. So that's what is happening here. 0, 0 remains 0, 0, but 1, 0 will be 1, 0. So which means that you are not doing any flip of this. It's a controlled NOT gate, and you are doing an Hadamard on this, right, later on. So you are doing an Hadamard operator on it. So you are doing a control NOT and an Hadamard. So this is before doing an Hadamard. From this you do an Hadamard, control NOT gate, you get this. After that you do an Hadamard, right? So let me look at this one example. You can see for state 0, 0, if you do a control NOT gate, nothing happens. But on 1, 1, you do a control NOT gate, it becomes 1, 0. So the output after this will be 0, 0, 1, 0. The output after you apply a control NOT on this. So which means that after this stage, that's what you are writing here. You have 0, 0. If you multiply them, this becomes 0, 0, and this will be 1, 0. Now it has been rewritten simply so that we can say, applying an Hadamard operator on the first qubit, you're going to get this as an output. Okay. So I think you can, if you start simply working out the mathematics, you'll start figuring it out. It's a simple one, simple algebra, but as nicely coming out as an output. So following this 4 steps. So this is one very striking and important example which interested people from computer science to look at these problems or expand these problems in more complicated way. Okay. So I think I will take another example now. I think if there is any question up to this point till superdense coding, it would be good. I think I can stop and take questions, and then we can go to another important example like this. So if anybody have a question, please unmute your microphone and then ask me.
Hello, sir.
Yes, please, yeah.
This is Moedin from Mahalingam Engineering College. Sir, can you take any one of the possibilities A and B,
Yeah.
for example 0 and 1,
Yeah.
and what we are getting in after step 3 and after step 4 with
Yeah.
the help of board, sir? Because
So you want me to do it right
is,
on the board?
yeah, sir.
Okay. Yeah, just I'll do that.
Any one example, sir. That is enough.
Yeah, yeah. Okay. So I'll just take this one example and then we'll do that. Okay. So I'm going to stop sharing the screen. Okay.
Sir, if you're writing under the board, it is not visible to us, sir. If you're writing below, board below, if you're writing, it is not visible to us, sir, yesterday.
It was not visible, is it? Okay, so
Yes,
let's
sir.
see.
Please write on the top of the board only, sir.
Okay, so I will try. Let's see. Just so is this visible?
Visible, sir.
Okay. So I think we'll take one example and then work out the full 4 state. So if Alice wants to send 0, 1, okay. So we'll take an example of 0, 1. So what they are sharing before is both Alice and Bob are sharing this. This is the state. I'm going to write them as psi. Okay. She wants to send 0 and 1. So my step 1 says that if my A is 0, you do nothing to this, which means step 1, you don't do anything and you are having the same thing as an output. Okay. So 1 by root 2, this will be 0, 0 plus 1, 1. Okay. So now step 2. Okay, what it says, if my state B is 1, then she has to do, or Alice has to do controlled Z gate. Okay, I think we looked at it, but I will do that operation here and we can see it will be 1 by root 2, 0, 0, right? And then you can see that it will be right? So it will be 0, 1. So here she's flipping the bit on her side, right? So it means that she's flipping both. Z is a flip operator, controlled flip. So the state 0, 0 and 1, 1 has become 1, 0 and 0, 1. That's all what she has done now. And she sends it to Bob. So I'm going to write as step 3 and step 4. So now it is with Bob. So Alice has nothing to do with it. So I'm just going to write psi with Bob. Right? What Bob will do is from this state, there is 1 by root 2. He applies a control NOT gate. What does control NOT gate says? If
Sir, it is not visible.
okay, sorry. Okay, I will try to. Okay, so if my first qubit is 1.
सर आप लेफ्ट मोस्ट पॉइंट से लिखना शुरू कर सकते हैं, वो पोर्शन है ना, दैट इज विजिबल.
दिस पोर्शन इज,
हाँ, दैट पोर्शन. सो आप वहां से शुरू करके इन तक आएंगे ना, तो देन इट इज विजिबल. यहाँ पे जो आपने साई लिखा है ना, द फर्स्ट वन, वहां से विजिबल है, उसके ऊपर वाला अभी विजिबल नहीं है. हाँ, जो आप मिटा रहे हैं वो विजिबल नहीं है अभी.
सो A and B is what that, and this we are calling it as 0 and 1 is what she wants to send, right? This is what Alice has to send. So So this is the initial state with the share, and then there is a step 1. Because the first bit is 0, she does nothing to it. The same thing will be there. But the second classical bit is 1, so she applies a control Z gate, which means that the qubit with her, she's changing the state of it, flipping it. So which means that 0 is becoming 1, 1 is becoming 0. So this is the flip which she has done, and now she has sent it off to Bob. Stop C. So now I'm going to write down what Bob on Bob's side. Now all that we have is psi at Bob's side. He will have 1 by root 2, 1 0, and 0 1. This is what he has got. Now what Bob will do is he applies control NOT gate on the state he has. That is what Alice has sent and together. So this will simply, what does control NOT do? If my first qubit is 1, the second qubit gets flipped. If my first qubit is 0, nothing happens to the second qubit. So here, this becomes 1 1, but nothing happens to the second part of the expression. So Bob got this state together, but he does control NOT operation on this, and he has done it. So now it's simple rewriting of this. We know, I think in one of the partial measurement explanation we were seeing, that I can rewrite this as 1 by root 2, 1 plus 0, tensor product of state 1. So it is the same thing. You're separating the first qubit and the second qubit, because second qubit is not, it has the same value on both the subset of the state. So now this, if you apply an Hadamard operator on the first, so it means that Hadamard on the first qubit and identity on the second qubit. This is what is the operation. And you have this output state, which will be 1 by root 2, 1 plus 0 into a tensor product of 1. So this is the state, and you are applying an Hadamard on the first. So it means that you can, I'll use a different color and show here. This operator is acting only on this part. It means that on the first qubit, this operator, identity, is acting on the second qubit. So nothing will happen to the second qubit, but the first qubit, you are applying an Hadamard operator, which means that becomes state 0 into state 1. So what Alice had to send was 0 and 1. All that she did was these two operations on her side, and then sending that bit to the Bob. And this is what we see on the Bob side. Bob, the moment he gets the first qubit also from Alice side, he does a control NOT operation, and then he does an Hadamard operator on the first qubit. This is irrespective of the state you want to send. I mean, you can send any other values, 1 1 or 0 0 or 1 0. These operations are independent of them. So he has no idea until he gets this measurement output that what operations or what was the state there in between. So does that make sense?
Excuse me, sir, what is the difference between step 1 and step 2?
Oh, step 1 and step 2?
Yes.
Okay, so step 1 is used to send an information, encode. Okay, what we are doing here is we have two classical bits, A and B. Step 1 is helping you to encode the information of the first classical bit into a quantum state. Step 2 is helping you to encode an information of the second classical bit into a quantum state. Since the first classical bit, information of first classical bit is 0 here, it is not changing the quantum state, which means that it has encoded, but you don't have to do anything. It says it's obviously there, you don't have to again encode it. But 1 information is encoded by making a small change into quantum state. So that's what step 1 and step 2 are doing here. Okay, so somebody is asking how many bits can be. So this is, as I mentioned, I'll change. Can I convert it to the slides now?
Yes, sir.
Okay. Okay. So you can see here, when I mentioned that the super dense coding here, it's a simple example. It's a very elementary example of sending 2 classical bits using a okay. So somebody wants again to let me see what was the last message. I think probably you can turn your microphone on and send. Okay, yeah. So somebody's asking me of the last step in the Adamant. So I will try to. So the state which Bob has after doing control NOT gate is 1 1 plus 0 1 by square root 2. This is the state which Bob has. Oh, sorry, it's not visible. Okay. So this is the state which Bob has after he does a control NOT gate. So now I'm rewriting this. See, when we said initially that a 2-qubit state is actually written like this, but in a simplified form, we write them together. So I have a provision here to rewrite this state as 1 plus 0 by root 2 tensor 1. So this is my first and second qubit. So now what is this in a matrix form, right? This is 0 plus 1 and 1 0 both are same, right? In a matrix form, this is this by root 2. Okay, tensor 0 1. This is the matrix form of it. Now what we are saying is applying an Adamant on this. What does Adamant? So we'll ignore this part because we said you apply Adamant only on the first qubits. I'm just going to show that one step, right? So my Adamant operator is 1 1 1 minus 1 divided by root 2, and this on 1 and 1. And this also is 1 by root 2, right? So 1 by root 2, 1 by root 2, you can always take them out, right? Or you can always multiply them. For the time being, we can ignore this point. We'll just do the multiplication of this matrix. 1 1, and this will be 1 1, right? So this will be 1 and plus 1. This will be 2, right? And this will be 1 and minus 1. So it means 1 minus 1. So this will become 0. We add 1 by root 2 here, 1 by root 2 here, and this becomes 1 by 2. So the output is 1 0, which is state 0. That's what the last step did here. So you are having the state, but then you rewrite them in it, and if you apply an Adamant on the first qubit, it means that in a matrix multiplication you are ending up with the state 0. Even when we were writing quantum circuits, so I was telling that you have Adamant operator 0 becomes 0 plus 1 by root 2. right? This is two-way, which means that if I start with this state, I apply an Hadamard operator, I'm going to get state 0. If I start with this goes with state. So one of the interesting thing about this unitary operators is they are reversible. So you can actually take an inverse of those matrices and then you can work back. That's why we take complex conjugate, adjoint things and all in the operations. So you can always do this simple reversible Hadamard operators and then get the state you want. Okay. Okay, so I think I will. We will probably ask another interesting question related to teleportation. Okay, I don't know. I think I'll just introduce the problem. Probably we'll take that up in the next session because it might take. Again, it's the same way it's involved as the super dense coding. But an introduction to this is very important. You might all have been very familiar with this sci-fis where you can teleport something. Teleport means you're not physically transforming. You're just making something disappear at some point and then make it reappear at some other point. Right? So that's what is the whole teleportation is about. But quantum teleportation does something like that. Surprisingly, that you can actually teleport a quantum state from some point to the other. It's not like teleporting an object from a point to point B, but an information of something. Like, if I say A and B, there's a classical bit information here, right? What we discussed in super dense coding. It can be a classical bit. You can encode them into quantum bit form and you can teleport them. Or it can be any information. If you can encode them in the form of quantum states, then you can teleport from one point to another. So instantaneous teleportation. Okay. So here we are doing it completely. We can look at this completely from a quantum circuit form directly to begin with. I didn't want it to have a statement of it and then mathematically describe and then go to a circuit. Let's say in a simple circuit form, you begin with in this way. It's the same way we had it in super dense coding, right? You can actually see Alice here is slightly different. Alice has a quantum state psi, which she wants to send to Bob. Nobody knows, I think even she might not have a complete information of it. It can be in superposition. Yes? Hello? So I think there was, okay. So in this whole of the circuit, Alice has some state psi. After doing some set of operations, Alice has successfully sent that state to Bob. It is a process of teleporting them. So she has teleported it without physically transforming set of information here. Okay. So it's defined in this form. Let us assume state psi. It can be any value, alpha 0, beta 1. And the starting state is this. So you are beginning with, hello? Is somebody saying that it's not audible for others?
Oh, audible, sir. Audible, sir.
Okay.
Audible, sir. Audible.
Okay. So here you have, so this is what we say, there is this state psi. Similarly, in the same way as we had in super dense coding, Alice and Bob in the beginning itself shared an entangled state. So this is a representation of an entangled state shared between Alice and Bob. So that's what I mentioned when we were talking about super dense coding also. In a state preparation, initially itself, Alice and Bob can share entangled state. Now they can decide whether they want to do super dense coding or they want to do quantum teleportation, or they can do many various different things on it. But as an initial state, they both share an entangled qubit, and Alice now wants to teleport a quantum state from her side to Bob. So it's just rewriting the complete state here in a form of 3-qubit system here. So you have alpha 0, 0, 0, alpha 0, 1, 1, 1, 0, 0, and 1, 1, 1. Okay. Now you can see simply here in the circuit, the first step would be The moment they decide what state to be sent in the entangled state is to do control NOT operation from the Alice side. Now you see Alice actually has 2 qubits on her side. So there are totally 3 quantum bits in this system. Alice has 2 qubits on her side. Bob has 1 qubit on his side. So totally it's a 3 qubit quantum system. So Alice does a control NOT gate on the qubit on her side. So, which means that you are only doing operation on the first 2 qubits, nothing. I mean, third qubit is not even touched. Whatever is there, you simply write down. When you are not doing anything, it means that it's equivalent to an identity operator. You're just keeping them the way it is. So here you see 0, 0, 0, nothing. But here you have 0, 1. This also nothing changes because your first qubit is still 0. But here, your first qubit is 1. And even here, your first qubit is 1. So you are changing, you are flipping the second qubit on them, and that's what the output you get. 1, 0, 0 becomes 1, 1, 0. 1, 1, 1 becomes 1, 0, 1. This is the step here. Alice does a control NOT gate on her side. And an Adamard operator to do this operation. Okay. So I think there are some comments been coming. So if there is something important, you can actually turn your microphone and then tell me how long it takes to do the teleportation. I think no, I'm going to just define here up to this point and we're going to stop because there are different cases to be discussed and we'll take it up after a break of 30 minutes. Okay. So I think I just said here we will do the control NOT gate and defining teleportation, and we can come back at 12 o'clock and then analyze quantum teleportation, output of it, all the steps out of this process. Okay, so is it okay, so Mahalakshmi madam, to stop at this point? And
Okay, sir. If you want to
or
continue.
if there is any quick question before we conclude for a small break.
Sir, participants, if you have any doubt, you can clarify it, sir.
Yeah, that's what. If anybody has any specific doubt up to this point.
Sir, it is regarding the entanglement. Again, I'm asking the question. What is the physical meaning? Can you just explain? Sorry, I have missed that part. That's why I'm asking.
Okay, so what has happened when people were looking at the quantum physics at the early stage is that if there are some unique way that 2 quantum systems are prepared together, they exchange some information between them. And when they are physically separated, any changes you make on one part of the system, the other part also automatically gets affected. So that was the initial motivation for people to think of the possibility of entangled state. It was actually called as EPR paradox. Einstein, Podolsky, and then Rosen. So these are 3 physicists. Einstein, you all know, and the other 2. They called it as a paradox because how can it be possible? There is no exchange of information between both of them, the 2 particles or 2 atoms which are prepared at some particular state. When they are physically separated, any change you make on one of the system automatically changes. When we say change, what does it mean? It means that a quantum state is modified. Right? It can be a photon where polarization is changed. Other one automatically changes its polarization. If one of the one of the atom goes from ground to excited one state, instantaneously other atom will change its state in some other way. So this strange phenomena was initially called as paradox because they could not believe that something like this can really happen in a physical world. And they thought there is something they don't understand. But over decades, people tried to analyze it, and then they say there are physical systems where this kind of behavior is seen and it has been established, so we need to take it as a nature given gift, right? So that's where it is there. I mean, one can actually, it's very difficult to explain more than, but what has happened now when we are trying to look at quantum computation or a quantum information theory, and we have learned even to create such kind of states. As I said, we can now use a control NOT gate and Adamard, and you can actually entangle these 2 systems. Initially, no relationship between them, but then you can entangle these 2 systems. So what it says, I mean, the take-home message would be you can actually create a quantum state, you can physically separate them, and then any change you make on one system, the other one will automatically change, which means that, or in a simple term, if you are looking at the slide in front of you, I'm just showing you one particular state. This is an entangled state here, right? Now, Alice makes a measurement on the qubit with her. So which means that the moment you make a measurement on a quantum state, which is in this form, it collapses to 1 by root 2 0 0 or 1 by root 2 1 1. Bob does not do anything. But even if Alice makes a measurement, it collapses to one of these two. Bob might be in some different part of the world. Still, it collapses to one of them. Then Alice clearly knows that if she gets state 0, Bob also has got state 1. If Alice gets state 1, Bob also has state 1. She doesn't even call Bob and ask, what is the state with you? She instantaneously knows what is the state with Bob. So this state can be seen as something which are physically separated, but now we know quantum physics collapses the state to one of these two forms once you make a measurement. Then without even asking Bob, she has an information of what is the state with Bob. I think that's something which will take some time to get into you, probably getting yourself more used to seeing these states and understanding measurement. You'll start appreciating it. That's a basic idea of entanglement, and you can create them. People now have created, physically separated them across 100 kilometers, hundreds of kilometers, and exchange information over last decade. Okay, so if there's any other.
Thank you very much.
Yeah, somebody's asking, is this entangled state can be used to seed security? And no, I mean, all of this quantum communication, quantum security, there are a lot of things. People initially could say that you can't, hack entangled state quantum communications via entangled channel, because the moment you make a measurement, Alice and Bob will get to know eavesdropper thing. But people try to use quantum state itself to go in between and try to hack. Then there has been measures to look at it. So it's all an evolving field. But a quantum state cannot be intercepted using classical methods. So that is something very clear. So it is a quantum security using quantum states or quantum entanglement is unhackable using classical methods. You need to use some quantum methods, but then there are already people who are looking at those problems in more intricate way. It's not very trivial. Even quantum methods can only do some partial things, and it's an evolving field. I think that itself is a field on its own right, but it will be interesting for people who are into security business to take into detail of it. Okay, so if there is no other question, or if there is any other question, I can take that.
Sir,
yes.
Can we quit the session? Sir, whether anyone have doubts? So someone is asking. Someone chat session. One is asking questions.
Alice information will get leaked, isn't it? No, the problem is, what if entangled state get hacked? The moment entangled state get hacked, it collapses. The moment you have a collapse in the quantum state, then they get to know it has been hacked, so they can discard this information. They won't even treat it as. So I think I'm not. There are examples for it. There is a simple BB84 protocol, what we call as quantum teleportation protocols, where these questions can be answered very explicitly. But since this session is completely on quantum computation, I'm not taking that example and not be addressing, but there are ways to look at all these things, how you understand it and immediately abandon this information and handle it. Okay, so
okay, sir. You can quit this session and we'll start after.
We'll come back at 12 o'clock and then we'll continue with quantum teleportation.
Thank you, sir. See, I had sent the attendance form in your chat session. Please fill the attendance session during the break.
Ma'am, repeat. Pardon, ma'am.
See, I had sent the attendance Google form in your chat session. Fill your attendance form for morning session.
Oh, madam, send us again, madam.
Sir, I will share the recorded video if possible.
Yes, madam, but it's not something.
So what you are asking me?
Hello, good morning, madam.
Yes, sir.
Hello, good morning, madam.
Yes, sir. What do you want?
Actually, the Google form attendance form is not accessible. It is giving a
Sir, your sound is
server
echoing.
not.
I'm not here.
Madam,
madam,
the
chat
Google
வந்து
form is not accessible.
Google form?
Is not accessible. It
Oh,
gives
now
a
you
server
can
not
access,
found
sir.
error.
I opened the access, sir.
Okay.
Thank you, sir.
madam, can you send the link again?
Again, I'll send in chat session, sir.
हाँ बेटी ऊपर क्या
So I can have break for half an hour, sir. Again, we will join at 12 o'clock.